Hello. Okay, so today we're going to go over Chapter 15, Lecture 11. So here's our pre-lecture video. We're going to talk about equilibrium, some more, kind of the whole theme of Chapter 15. So we're going to first look at homogeneous versus heterogeneous equilibrium. So homogeneous equilibrium is when we have everything in the same state. So everything within our equilibrium reaction is in the same state of matter, whether it be gas, liquid, aqueous, doesn't really matter. So all species are in the same state of matter. So something like this: H2 gas plus O2 gas, H2O gas. So everything's in the gaseous state, so it would be homogeneous. Next we have heterogeneous equilibrium. And this is when we have different states within here. The dissolving of a solid would be an example of a heterogeneous equilibrium, something like this. PbCl2 solid going to Pb2 plus aqueous plus Cl minus 2Cl minus aqueous. So we've got a solid and two aqueous species, so this would be considered a heterogeneous mixture. So far, we've mostly looked at homogeneous equilibrium, and we've looked at, A plus B goes to C plus D. All of those things are in our equilibrium constant expression. However, things that are in the solid state, or things that are pure liquids, so pure solids or pure liquids, will actually will not show up in equilibrium expression. So species that are pure solids or pure liquids, so those that have an S or L as a subscript in parentheses, will not show up in the equilibrium constant expression. And that's because we're not looking at a changing of concentration with these, right? They're not, they don't have variable concentrations because they're pure substances, right? And everything within equilibrium constant expression should have the ability to have the concentration change. So if we look back at this PbCl2 solid, we think about its Kc will actually just be Pb2 plus Cl minus squared. We will not include that solid term in that equilibrium constant expression. Also note with equilibrium constant expression in terms of pressure, I've said this already, but just in case, we will only put in terms that are gaseous in nature. Okay. So let's think about our equilibrium constant a little bit more. So if we have if we have all of our equilibrium concentrations or all of our equilibrium partial pressures, we can determine our equilibrium constant. So as long as we have all of those equilibrium concentrations or equilibrium partial pressures, we can put them into our equilibrium expression and solve for our Kc or our Kp. For instance, if we have something like N2 plus 3H2 going to 2NH3, we would write that equilibrium constant expression. I'm going to put it in terms of pressure. We would write it as NH3 squared over N2 H2 cubed. And as long as we have, oh, excuse me, I did that all wrong. This would be Kc. Or we can write it in terms of Kp with our partial pressures. So if we have all of our equilibrium concentrations or equilibrium partial pressures, we can determine Kc by just placing these in, and then Kc or Kp will be unitless. Okay. We can also, if we have our Kc or Kp and we're just missing one of the substances, we can also solve for it. So we can solve for one concentration, equilibrium concentration specifically, or one equilibrium partial pressure, if we have the other equilibrium values and the equilibrium constant. So we can also take these equations written here. If we have two of the pressures or concentrations and we have Kc or Kp, then we can solve for the last one just by doing simple arithmetic. Last thing we can do, well, another calculation we can do with this information is we can determine our equilibrium concentrations if we have our initial concentrations and our Kc value. So this is when we're going to start using what's called a Rice table. Put the R there. So used to determine equilibrium concentrations or pressures when the initial concentrations or pressures are known, along with the equilibrium constant. Okay, so the Rice, the R is reaction, the I is initial, so this would be concentration or partial pressure. The C is going to be change, and that's in concentration, partial pressure. And then E would be equilibrium. So for instance, we have a reaction H2 gas plus I2 gas is in equilibrium with 2HI gas. In this, we would be given our initial concentrations of our two species, so or two reactant species, so 1.0 times 10 to the negative 3 molar, and 2.0 times 10 to negative 3 molar. And then initially we have 0 of this. We're also, so we're given a equilibrium concentration of HI of 1.87 times 10 to the negative 3 molar. So this is one thing that could be given with a Kc equal to 51. Okay, so this is an example of something that could be given. An initial concentration of the two reactants, an equilibrium concentration for our product, and an equilibrium constant. So how we would use this table is our change, we're going to use x's. So anytime we have 1 mole of a substance, we're going to call it x. 2 moles, 2x. 3 moles, 3x, so on and so forth. We either add or minus depending on our stoichiometry. So in this case, H2 has 1 as a stoichiometric coefficient, so we're going to use x. Same thing with I2. But our HI has a 2 as a stoichiometric coefficient, so we'd use 2x. So when we go from our initial reactants to producing HI, we're going to remove however much H2 and I as we produce HI. So we'd say minus x for H2 minus x for I2, because we're going to remove that amount, and add 2x to our HI. Okay, so we subtracted 1x from H2 and I2 because they're both 1 as a stoichiometric coefficient, and as we change, or as we shift, and we go from our initial reactants to reactant plus product in our equilibrium expression, we're going to add 2x to our HI. And then our equilibrium will be 1.0 times 10 to the negative 3 molar minus x for H2, 2.0 times by 10 to the negative 3 molar minus x for I2, and then our 2x is equal to 1.87 times 10 to the negative 3 molar for our HI. Okay? So at equilibrium, we have the following concentrations. Our H2 has a concentration of 1.0 times 10 to the negative 3 molar minus x. Our I2 has a concentration of 2.0 molar, or 2.0 times 10 to the negative 3 molar minus x. And our HI has a concentration of 2x, which equals 1.87 times 10 to the negative 3 molar, because this value was given as the equilibrium concentration. So, it's actually a pretty easy way of dealing with this. We would say, okay, I've got this equilibrium concentration, and I have these x values. If 2x equals 1.87 times 10 to the negative 3 molar, x would equal 9.35 times 10 to the negative 4 molar. And then we're just going to take that x value and put it in to solve for our H2 and our I2. So this value is going to go in for these two x's, right here and right here. And we would say we have H2 concentration equal 1.0 times 10 to the negative 3 molar minus 9.35 times 10 to the negative 4 molar, giving us a value of, sorry, I wrote this down somewhere, 6.5 times 10 to the negative 4 molar, and then our I2 would be 2.0 times 10 to the negative 3 molar minus 9.35 times 10 to the negative 4 molar equal to 1.065 times 10 to the negative 3 molar, and then our HI is equal to 1.87 times 10 to the negative 3 molar. Now, since we already have our Kc value, we can put these values into our equilibrium constant expression and compare and make sure that it makes sense. So, take our Kc, is equal to our Hi squared divided by H2 and I2. So it's going to equal 1.87 times 10 to the negative 3 molar squared divided by 6.5 times 10 to the negative 4 molar times by 1.065 times 10 to the negative 3 molar. And when we solve for this, we get a value of 51. You can use this information either with or without the equilibrium constant at the beginning. If the equilibrium constant is given at the beginning, like I gave, right here, then you can compare the values and make sure that they make sense, and they do. Or you could have just been given this information right here, and you could solve for your Kc. Okay? that is everything.